Okay, so you can see my screen and I'm audible, right? So, very good evening, friends, and welcome to the webinar. Our topic for today is Scikit Learn Transformation. Okay, so when we are talking about this transformations, and this is most important point when we talk about data pre-processing, right? So data pre-processing is one of the time-taking, very crucial steps for any project, for any ML project. So when we talk about our real life data, right, we say that it is very, very messy. It's not organized properly. So there is no meaning in making a machine learning model without our pre-processing. We first pre-process our data. You feed that processed data to machine learning models for very good performance. So one such is the transformation. We talk about the transformation, right, which is feature transformation. So it is a technique, or we can say it is a mathematical transformation or a pre-processing technique to make something, which is not perfect. We are trying to do some changes to make it perfect. So what is making it perfect, not perfect? It is nothing but you are trying to improve. Finally, at the end of the day, we want model performance. So we are applying some math formulas here to your dimensions, or I can say features or columns, transform the values which are very useful for our further analysis. So there comes the picture here, our feature engineering. So whatever features, the raw data you have, you do a lot of feature engineering. What is meant by feature engineering? Whether all the inputs you have collected, are they relevant or not, right? So these relevant data, is it correctly fitting our model? Does it really make sense to use all these features? And doing a kind of feature engineering will improve the accuracy of your model. So as we work with not a single set of algorithms, we have various algorithms, different types of algorithms, where you need to apply some transformations to make your accuracy better. So this can be done using different techniques. So it can be called as feature engineering, or we are trying to reduce your features. You may combine multiple columns, you may apply some log transformations, or you divide one column with other column, so that you want, according to principle of parsimony, we say sometimes, simpler the model, better the model, so performance will enhance. So it helps our algorithms to converge faster. Converge faster means to reach to a point where you have less error. Quickly it will reach to the convergence point. So next is, why do you have to do this transformations? Is it mandatory every time? Of course, yes. My answer would be yes, because linear logistic regression, right? They have these algorithms. We have these algorithms where we are trying to do some kind of normal distribution, right? A kind of normality check, which is a mandatory thing here. So when we are talking about these mandatory things, definitely one thing is normal distribution. Check the skewness, right? So for linear regression, if the data are not normal, normal means a nicely, a bell-shaped curve, I can say equally spaced from 0 to negative side, 0 to positive side, right? So more likely, definitely we are lucky if at all your data is not skewed. But if at all is skewed, we need to go, the only weapon we have is transformations. So by applying some transformations to these features which are not normal or which are skewed, right, we apply some kind of technique, right, called as transformations. What is the main thing here? Because linear regression will only give you better accuracy, better performance if the data are normal. If the data are not normal, you will end up with worst scenarios. So what will you do here when we are doing this? Right? When we are doing this, there are many other techniques are there. We'll see few techniques here, which is very, very important for us as a goal. Why we want to do these transformations. Right? So normal distribution is very, very important, which is, the key point. The statisticians say that yes, it is mandatory. Why do they stress that point? Because the statisticians, researchers who all worked, they assumed that everything is normal. But in a real time scenario, not all things are normal. Most of the things are not normal. Hardly one or two inputs what we collect are normal. Right? And you check this normality if the data you have collected are continuous. There is no question of discrete data to be checked for normality, whether it is age, whether it is income, whether it is a height, whether it is a speed, whatever inputs you take, it is checked that the data are normal or not. However, it is a best practice and we don't know what is underlying the pattern here, but we want that it should be normally distributed. To our surprise, there are many techniques are there where we apply transformations. You are changing your data using that transformed data as an input. So today we will discuss few transformations. There are 3 best transformation techniques which will solve our problem and make data normal. So one is our choice. Give a try with the second transformation. Give a try with third transformation so that you make your data normal. The first is function transformation. What is it actually? You can write your own logic, means own way of writing. You can define your own function. You want to apply log transformation, reciprocal, square root, cube. You want to transform it. So suppose you have a column called weight. Weight is not normal distributed. It's not a bell-shaped curve. But you want to make it normal. What will you do? You make log of weight, weight to the power of 1 by 3, weight to the power of 3, weight to square, square root of weight. All such transformations you put under a tag called function transformation. Right? So it is not restricting ourselves for one technique. Many techniques, our aim is to make it normal. Whether you may have right skew, left skew, but ultimately if you apply some transformations, what will happen? Your data would become normal. That will be your column. The previous columns, whatever you took weight, that will be deleted. Weight square is giving you normal data output. You take weight square as an input. The first one, weight, will be deleted, ignored. So generally these transformations are very, very effective and many things will fall in place if at all you're applying transformations, but it is a mandatory step for us. So the transformation technique, this is mostly log transformation is something what we have experimented that for right skew data, this would work good. Right? So when you are doing this, you can apply a reciprocal transformation. When you say reciprocal, if at all your data holds some 0 values, it will not work. Right? So what you will do here is...
Ma'am, I have one question.
Yeah.
When to apply this transformation, like kind of like log transformation or reciprocal or scale? Like how do we?
Whenever you have to check whether the data is continuous. If the data is continuous, you have to check for normal test. Normality. Normal. If the data is continuous, like weight, age, speed, whatever, we never collect continuous data. It is mandatory that it is continuous. Data should be normal. Exclusively, if you are applying regression technique, it is very important. If you just ignore that point and you go and build your model, it will result in wrong analysis, wrong results. Everything will goes wrong because statisticians have given few algorithms for us, assuming the data are normal. Okay, your results will hold good.
Any thumb rule that, like, for example, let's say if the data is left skewness or right skewness, so like
I'll
which
show you in the plot.
transformation? Yeah.
I'll show you in the code. Yeah, just hold on. 2 more slides. I'll explain you in the code part how it
Okay.
goes.
Yeah. Okay.
Yeah. So when you talk about the transformation, reversing a transformation, it cannot be used for variables with zero value. So you feel that okay, reciprocal would not work for that. Then you go and apply square, right? Or you apply square root. So different types of skewness, it's like a trial and error method. Sometimes for one column one might work, for sometimes the other thing other might work. There is no fixed rule or no hard and fast rule that if it is right skewed, only apply square root. If it is left skew, only apply square. There is nothing hard and fast rule here. Anything you can apply, it's like making the data normal. Okay, it's like custom transformation. Then the next transformation is a par transformation. Par transformation is when the desired output is Gaussian distribution, these transformations are used. There is something called as heteroscedasticity. What is that? When you are calculating errors, if the same model is working differently for one person's data and it is working differently for other person's data. Okay, if the same model is working differently for me, it is giving me less error for my data. If I pass my data, my weight, my BMI, it is saying that I am obese person. For you, you are passing your weight and your BMI, it is saying less obese. Same model, it is working differently for two different people. That is called as heteroscedasticity. So what you will do, that is with such situations, power transformation would work. So this power transformation will give you two different techniques. One is Box-Cox and Eo-Johnson. When do you use Box-Cox and when you use Eo-Johnson, certain criteria is there here. If your data, that column what you are taking, if you have only positive values if you have, then only you'll apply Box-Cox transformation. Even zero is there, Box-Cox will spill out error. It will not understand what to do. What is it you are passing? Eo-Johnson transformation, it will take along with zero and negative values also as input. So you will check now when you do your described function in your Python, you get to know what is a minimum value, what is a maximum value. Then you can take a call. You want to apply Box-Cox or you want to apply Eo-Johnson. Okay. Then finally you have one more, which is nothing but quantile transformation. Exclusively we talk about quantile transformation, which is a non-parametric data transformation, right? For your quantitative data. Quantile, when we talk about box plot, usually when we talk about outliers, we have used this term quantiles, right? This quantile transformer can transform the data into normal distribution. It depends upon your interest. Any nonlinear method, it may distort your correlation when you are measuring on the same scale. When you have outliers means definitely you have a very, very long tails. Long tail means skewness is there, right side or the left side. You can go for quantile transformation to reduce this problem. So it is nothing but it will work like a cumulative distribution function, but in an inverse manner. So quantile transformation is definitely used when you have outliers. Like when you plot a histogram, you got to see that entire data is one side and you have the other data, only one or two data points are out of scope. Like we have all our friends sitting, eating together, drinking together, playing together, studying together. But there will be one or two people, they never mingle with any other people. So that time how your data looks like? Your data looks like this. Or your data might look like this. But we want a bell-shaped curve equidistant like this. It is a bell-shaped curve. If the data is not like this, you are applying all these transformations. It's up to us now. Whatever transformation technique we can use, and for every column you have, you can apply different transformations. Right? So let us understand this with the Python code. So I'm using Google Colab here to understand how you can apply transformations. So when we are talking about any pulling the data, right? This transformations. Let me pull the data first. Pandas. I want to plot because I want to check whether the data are normal or not. Matplotlib.pyplot as PLT. Then I have NumPy. Then Seaborn package for plotting. So all these transformers are available for us in sklearn.preprocessing. So sklearn is the main module. In that submodule is preprocessing. You are importing function transformer, as I told you, power transformer, quantile transformer. Okay. Now what will I do is I'm just
Yeah, one small doubt regarding. I mean, when we need to use this Seaborn and Matplotlib, ma'am.
Matplotlib is a package which will give you normal general, like I can say you have a normal calci, right? When you have a normal calci, what we have used in intermediate like that. That is your Matplotlib. When we came to engineering, we had very, very efficient calculators, right? More
like
all that, more impressive, more clear, or pleasy plots. You use Seaborn.
Okay, ma'am. Thank you.
Okay, when you do this now, I want to split my data. I am using, because normality test is checked for data being continuous. If data is continuous, you use regression models. So I'm using two regressors here to compare whether which model is giving you better accuracy. Okay, random forest is one regressor, one machine learning. KN and neighbor is one more regressor. And pipeline is a module or a function. You can write multiple steps in that pipeline. When you use a pipeline function, whatever you want to do scale transformation, you want to fit your model, you want to check the result. Multiple lines of code, you can write it in a tuple and you can use this pipeline function. So let me run this first one. So then I'm running this. So we will use an inbuilt data set which is available in sklearn, that is the fetch California housing. This is the data set.
Excuse me, ma'am, I had one doubt.
Yeah.
Ma'am, you said for pipeline function that we can add multiple lines of code inside the pipeline function and then we can execute it together.
Yes.
So how different is it from user-defined function in which we write like good part of the code?
No. Whenever you write a user-defined function, any function which is given inbuilt by Python, you can write it as custom-based function. Only difference is that if at all you are using a pipeline function or a like print function, int function, any function you use, if at all you want to use multiple times, you have 1,000 lines of code. Okay, you want to do one single change, you have to check that where did you use that pipeline function, you have to do it. Otherwise, if you take your custom-based function, if you write it, that function, you'll go to that function directly and you'll do a change.
Right.
So multiple changes can be done within no time when you write your own logic functions. If at all you are using inbuilt functions available, it takes time for any small change also.
No, so what is the advantage of pipeline function over user-defined function in this case?
No, there's no advantage or disadvantage. Both are do equally. But pipeline function is inbuilt. You are not writing any custom-based function, right? You are not writing any logic. Directly it is there, you are using it. If you don't want to use it, you can leave it. But when you want to use custom-based function, you have to write your own logic and then pull in your that lines of code to it. Right?
Okay.
So always we suggest that for small changes, we use custom-based functions, like small logics you can write, because it will not make your model complex or code complex.
Okay. So like in case of random forest where we use like
scaling.
Different models we use in case of random forest.
Ensemble models, not random forest.
Yes. ensemble technique. So in that multiple models are used. So can we use pipeline in that case also?
Yes, yes, I'll show you. I have used it. No? I'll show you.
Okay.
I'm just
Thank you.
fetching the data here. Yeah. Yeah, fetching the data here. Let me show you how it looks. Right? So I'm having latitude, longitude, population. So they are all continuous data. Right? We are not bothered about what are all these. We are only checking how it transformations are applied. And my Y column is this one. It is met house value of the house. I just removed these latitude and longitude. Okay. So I'm going to index location, all the rows. -2 will remove that last 2 columns. Okay. And head function, you can see that those 2 are gone. Then I'm just showing you describe function is the first step what you do. Whether you want to scale your data, you don't want to scale your data. You might be knowing now that these are the output of a box plot, right? More than a box plot. Count and mean are also coming here. It mostly is your like Q1, Q2, Q3, maximum value, minimum value. So definitely most of the things are not in space here, not in range. Okay, definitely scaling is important here. Then the second thing is I'm splitting my data using train test split x comma y. Test size is 0.2. So 80%, 20% ratio, we are dividing it. Okay. So what did I do to run multiple code, multiple columns are there, multiple graphs I have to show. No? For that I have written a custom function so that I can use this plots function. I can pass my data. I can pass the column names and which transformation I'm applying so that the change in the output I can observe. Okay. Change in the output I can observe. When we are doing this, when we do this, it is easy for us because we have written I can use matplotlib and do it. But why did I write a custom function? Because I can use, this kernel density estimation. I can just say a subplot. I can give a title. So I can make it easy according to my own way I want to plot it. So I am just saying I want to figure sizes this much. I want the density estimation. Take every VAR from the data set, every column you take, you just plot it in the x-axis and y-axis. Plot title. Okay, before transformation, after transformation. So in the second line of code here, I have just applied fit underscore transform. So I'm just doing some transformations. Here, this logic will work without transformation. This plot will show you another subplot with 122. Figure size is same, but I get a different plot after transformation. So when I run this, my function name is plots. I use that plots now. So what I'll do, I'll take all the columns in the train data. For every column in this, iteration should happen for all the columns in the train data. Plots. What is this plots? This custom function what I have used. Plots. Pass my train data df. var is col. Functional transformation here. T is here. This T will be no functional transformer. I am applying square root of x transformation for my data. Now you get the plots for all the columns. See here. See. This is a skewed output. Okay. This is a skewed output. Now after applying, little bit skewness got reduced. So this is the density what I have used for KDE. See the skewness here if you see this part and this part, it got reduced. So not all the columns might solve the problem here, but at least few columns. See here, it did not work well. See, little bit peakness, peak here and peak here got changed. After applying square root, your square root got changed to this data. This is applying root of k. See this peakness. So making it normal is you want a bell-shaped curve, totally like this. At least this is better when compared to before applying transformation. So few columns, applying on every column, checking it, this way will work doing this. If you want to apply x 1 by 3, np dot power x 1 x comma 1 by 3. For every column it will do. You have to again check the transformation. How is the output? How is the skewness? See here, it's trying to become normal but not effective way. See here, little bit change you can observe for this column like this. So these are the different ways of doing. You can do now log transformation also. All these are functional transformations what you can apply. So it's just like trial and error method. For one it might work well, for other it might not work well. See here how much change it became, different skewness here. See here, wonderful. This one. See the bell-shaped curve? Nice. Equidistant from here and here. Little skewness is there. So like this, what we will do, we can apply different transformations here. Right? So if you apply transformations, this is your original data. This is how it looks. Once you apply transformations, this is how it is working. What did we miss? Oh, did not run this. So this is how the transformed data is. From 6 it became this when you applied this transformation. X to the power of half my square root. Okay. Now what will I do? I'll write a custom function. Okay. I'm saying my function name is model accuracy scale. Okay. This is MOD. So I can give any model to. So what am I doing? I'm using a pipeline function. I'm saying that you scale it. Okay. What is the scale and what are you writing here? In the tuple you are writing use log of LP. From NumPy, take log of LP. Give me the output. Once you get it, you can fit it. So one transfer only I'm applying. I can apply 2, 3, but I want only one because I don't want to make it clumsy. So many columns are there. Model.mod, model underscore scale dot fit. I'm fitting my model. I'm asking me it to return what is the accuracy of the model if I apply log transformation to my data. Okay. Then if I don't scale it, if I don't apply this function transformation, knowing that they are not normal, I'm just going and building the model. See here, they're directly pipeline and I'm just saying model. Okay. I'm just doing this model. So what will happen here? I'm saying that return me unscaled score. So when I don't apply transformation, what will happen? 2 models I'm building here. Okay. Now I'll use this model underscore accuracy underscore scale. I'm using KNN. So what transformation I have applied? Log transformation I have applied. See the accuracy I got? 61. But if I don't do transformation, right, I'm going to get this one. 0.17. See the accuracy? So what is that you are doing here is, when you apply a random forest regressor, check the accuracy. When you are checking model underscore accuracy underscore unscaled, see this, what is happening. Because random forest regressor does not bother about scaling and all that, the transformation is not required, you will not find much difference in the accuracy. But KNN is very, very particular about this, about applying transformation. So yes, definitely there is a change in the accuracy. Worst scenario here. This is good. It depends upon the regression technique you are using also. It depends upon the regression technique you are using also. So like that, if I apply power transformation, Box-Cox method, your Johnson method, right? Same plot, same function I've written for plots. I'll apply now plots instead of function underscore transform. Here I'll apply power transformer. So method equal to Box-Cox, you should write it. If you are applying your Johnson, not required because default is your Johnson. It will understand that okay, it is your Johnson transformation. But if you are using a different Box-Cox, if you have negative values, you have to use your Johnson. If you have only positive values, you use Box-Cox. See the plots. See, this is called as normal. See this, how much skewness it is there, long tail products, long tail this side. Now it got changed. How much time is getting saved for us? See here, for all the columns, you see, wow. Right? So few transformations would work for few columns. You can apply and you can check. You can check the accuracy. This is not working fine. Chalo, then you will use different one. See here. This is your Johnson. Or all the columns using for loop. See here. Such a transformer, power transformer changed this. Right? So this can be used only for positive values. As I told you, your Johnson can be used with 0 and negative values also. So now in the pipeline function, I'm using power transformer. Okay. In this unscaled, I'm not using any transformer. Without transformations, what will be the accuracy of my model? With the transformation, what will be the accuracy of model? So KNN definitely takes a call. Definitely it is required to apply transformation because the regressor does not understand things properly. It's mandatory to check that. See here, better than the previous functional transformer. Without scaling, without applying power transformer, check the accuracy. See, it was. But random forest, it does not bother much. If you do or if you don't do, because the settings, the model is built like that. The inbuilt functionality is like that. So for any, if the type of technique you are choosing, the type of model you are choosing, it's very, very important. Right? It will be same, more or less the same. Okay? If you apply now the same thing, right? You will find the difference. Just change it. Changing it. For random forest, the accuracies are same. Only thing is single line of code you are changing. You are applying power transformer, box scouts, power transformer, your Johnson. For unscaled, both are same because random forest is clever enough. Multiple trees are built. Decision tree regressors. Right? Same, 66.8, 66.8. When you apply a quantile transformation, right? When you check for quantile, definitely when you have outliers, you have this problem of quantiles. Quantiles, you check the quantile transformer. It is a non-parametric transformation technique. You have to check your numerical data distribution so that it follows normal distribution or not. So you are passing your data X columns quantile transformer. See here, before applying, after applying. See, this became like this. It works with quantiles. Taking the quantiles and it works. Right? So let us check the accuracy of this model. When you apply quantile, is there any difference? So distribution you are checking is normal. Instead of doing this plot also, friends, you can do your QQ plot to check how much skewness is there. But the accuracy is 63 only. If you apply quantile, there are the accuracy is worst for unscaled. Let's check for random forest. The random forest is not changing anything, but we are only observing a difference in KNN. So definitely we need to check for the data is normal or not for KNN regressor, but random forest is unaffected. You have applied any transformation, the accuracy is same. The major change in accuracy is only for your transformed and not transformed for KNN regressor. So different algorithms have different predefined things to be solved. So whichever is good, you can take a call on it. Right? So that is your Scikit learn. Using scikit-learn, you can apply transformations, friends. These are the conclusions here. So we have to apply. This is very, very mandatory step to check your normality. If at all you don't want to do any custom function also, right, go to Cborn package, matplotlib, directly you can take qplot, which is quantile plot, check whether the data becomes normal or not. So thank you all for joining in. Any questions? You can ask.
Ma'am, if it is categorical data, like what kind of transformation we have to use?
No, Maneru. It's only for continuous data. You check this process is applied only for y being continuous, x being continuous.
Okay, so in case of categorical data, it is not required.
Not required. Not required. No.
Okay.
You don't apply transformations only. Okay, we have a question here. Yeah, this Python code file. Okay, is there any option to share it across? Let me check. Do you have any option?
Share link for that, ma'am.
Okay.
Share link.
Okay.
Ma'am, if you have it on GitHub, then